And for the next type of fundamental particle, these are called leptons. We talked a lot about the particles that are in the nucleus of an atom. We talked about baryons, but what about these electrons and the particles outside of the nucleus? And those are made up of leptons. So leptons are fundamental particles that make up electrons. An electron is a fundamental. We haven't found something inside of it, and it's classified as a lepton. There's 6 of them. Okay, so electrons, we know that they exist. They're particles that are negatively charged, but we also recently found that the electron has a little flea, a little smaller particle that is flying around it called a neutrino. So each type of lepton has a flea attached to it. Okay, so an electron has an electron neutrino floating around it. A muon, which is quite a large, see that energy? It's much larger. It's a much larger electron. It's like huge, and it's very rare to find it. But they're around. Okay, so a muon, which is a very large electron, has a muon neutrino floating around it. And then a tau particle is really huge. It's a huge type of electron that exists for a short amount of time. All right, has a tau neutrino. So these are the most common ones that we see, electrons that have neutrinos floating around it. And we've seen them before in beta decay reactions. So in a beta decay reaction, you have a neutron in the nucleus that is being converted into proton. If you look at the baryon number, the baryon number here would be +1 baryon. Okay, because 1/3, 1/3, 1/3. And on the right-hand side, my baryon number is conserved because I have +1/3, 1/3, 1/3. Now with leptons, leptons don't have baryon numbers. Leptons have lepton numbers, okay? So each of these leptons has a lepton number of 1, okay? They are all leptons. They have lepton numbers of 1, okay? So the beta particle doesn't have any baryon number, so it's not going to contribute to it, but it has 1 lepton number, okay? And a neutrino normally would have 1 lepton number, but in order to conserve the lepton number on this side I don't have any leptons. So on the right-hand side, if I made a beta particle, I would have to conserve the lepton number by making an antineutrino. The antineutrino would have a -1 lepton number, and those would cancel out. So that's why we would make an antineutrino that you had to memorize with a beta particle, because it has to cancel out. Okay. Now, what about charge? The charge on this side is 0 if you add up the charge. Okay, if you add up the charge of a proton, the charge of a proton is +1 charge. Okay, so the electron comes off to conserve charge. The electron has a charge of -1. So the charge is -1 charge. And the neutrino, all neutrinos have a charge of 0, so they don't contribute to that. Even if it's an antineutrino, it has 0 charge. All right? So basically, we figured out where this antineutrino comes from. The antineutrino comes from the fact that we have to conserve the lepton number. We made a lepton, but there was no leptons on this side, so an antineutrino has to come out to cancel it out, so it doesn't disobey the conservation laws. So in summary, leptons are electrons, and all electrons have a neutrino floating around it. We have different types of electrons. These larger ones are more rare. They have larger electrons around it. In the data booklet, you have a table of leptons with their properties, the charges, so you'll know how to apply it for conservation rules. You most often see leptons associated with beta decay reactions. Okay, somewhere in a question they'd give you a beta decay reaction and ask you whether the lepton number is conserved in the reaction or not. Okay, does this reaction happen? In order for the reaction to happen, the lepton number needs to be conserved.